Our speaker today is Charlotte Aten from University of Rochester, and she will be talking on multiplayer rock, paper, scissors. Thank you, Charlotte. Go ahead.
Oh, thank you so much for having me. Uh, so first of all, can everyone see where I wrote New York Combinatorics seminar? Okay, fantastic. Uh, yeah, so today I'm going to be talking about a multiplayer version of rock, paper, scissors. And for those of you, I think there are at least a couple in the audience who have listened to me talk about rock, paper, scissors before. This talk has a more combinatorial focus and will include things that I've never talked about in any talk that you've seen before, I'm pretty sure. Okay, so, uh, oh, that's nice. It just clears for me. Okay. Um, I always start the story about my rock, paper, scissors project the same way. In the summer of 2017, I lived in a cave in Yosemite National Park. And while I was there, I wanted to explain to my friends that I study universal algebra. I realized that rock, paper, scissors was actually a particularly simple way to do that. And I'm going to be thinking of rock, paper, scissors in three different ways simultaneously. I'm going to be thinking of it as a game, as an algebraic structure called a magma, which is a set with a single binary operation on it. And I'm also going to be thinking of it as a sort of directed graph. And I'm going to be switching between all three of those perspectives throughout the talk. So for anyone who hasn't ever been exposed to this before, which I think is rare, but it happens, rock, paper, scissors is a game where two players simultaneously choose one of three items, which are rock, paper, and scissors. And then based on which pair of items were chosen by the players, that tells us whether one player won and the other lost, or whether they tie. If they choose the same item, they tie and no one wins or loses, depending on your perspective. And uh, and then for the other items, rock beats scissors, which beat paper, which beats rock. Okay, so we can actually view this game as a magma, which again is a set with a single binary operation, a single map taking pairs of elements of that set to other elements of that set, where f of xy is just defined to be the winning item from among x and y. So for example, as I was saying, paper beats rock. And so here we can see that rock times paper in this magma multiplication gives us paper. And similarly for the other things. So rock times rock is rock because we think of both players who chose rock as being winners, even though that's really a tie. All right, so I also realized that I wanted to be able to play with many of my friends at the same time. And this led me to study hypertournaments and hypertournament algebras. So for the rest of this talk, I'm going to be first of all defining rock paper scissors and pseudo rock paper scissors magmas, and then giving a numerical constraint relating the arity of these magmas with their order, and then finally, then I will define regular rock paper scissors magmas, and then I will discuss hypertournaments and how all of these things can be viewed as a sort of pointed hypertournament. And finally, I'll discuss an embedding result for hypertournaments and some open questions that I have. I don't know that they'll be difficult open questions, but they're questions that I haven't addressed yet. So what should it even mean to have a multiplayer version of the game rock, paper, scissors? Well, the game rock, paper, scissors, and I'll define all of these terms in a minute, is conservative, essentially polyadic, strongly fair, and non-degenerate. And these are the properties that we want for a multiplayer game also, or at least the properties that I want. Okay, so what does a multiplayer game actually mean? Well, I'm going to refer to a set A equipped with an n-ary operation as an n-ary magma. So this is just a set and some map that takes n tuples of A to A, where n is some fixed natural number. And I'm never going to consider n equals 0. That's not something I'm interested in. So the selection, okay, so then any n-ary magma can actually be viewed as a game. It can be viewed as a game that I call a selection game, where this game has n players, which we'll call P1, P2 through Pn. Think of n people sitting at a table, and they each have their place at the table. Each player, Pi, simultaneously chooses some item, Ai, from the collection of possible items, which is our underlying set A. And the winners of this selection game are all the players who choose F of A1, A2, up through AN. So that's a pretty broad class of games, but these are games in the game theoretic sense. And of course, I don't want just any selection game. I want one with a bunch of special properties. So the first property that rock, paper, scissors has is conservativity. An operation taking n tuples of A to A, or an n-ary operation, is conservative when given any n tuple of things in A, we have that its image actually is in the set of elements in this tuple. So a conservative operation always picks out one of the arguments that it's fed, and that's the output. It doesn't have to be the same one, so it doesn't have to be a projection operation. It just has to pick one of these guys that were fed into it to begin with. So we say that the magma is conservative when each round has at least one winning player. So that's the motivation there. It's not much fun to play a game where most of the time nobody actually wins. That's kind of silly. So our second property is essential polyadicity. We say that an operation is essentially polyadic when there's a map taking subsets of A, this is the power set of A, to A, which agrees with F in this manner. So in other words, the operation F is essentially polyadic when its value actually only depends on the underlying set of arguments fed to it and not the order or the multiplicity of arguments, as long as at least one appears. And so this property is doing a lot of work for us. It's telling us both that we don't have to keep track of the number of times each item was played, only that at least one was played. And I want that because I find it annoying to have to sit there and count whether 45 or 46 people all chose scissors. That's excruciating. And also it tells us that it doesn't matter what seat you have at the table. Any permutation of the positions of the players will still result in the same output. So you aren't doing any better by sitting at a different place at the table. The third property that I would like is strong fairness. And this is sort of the most opaque to define, I suppose. So the idea, I guess, before I say formally what it is, the idea is that each item should have the same chance of being the winning item when exactly k distinct items are chosen for any fixed natural number k that you choose. So for example, if I'm playing a game with 100 people and maybe 101 people, and I consider all of the possible situations where exactly 16 items are chosen, I want each item to have the same chance of being the winning item from among all of those situations. Note that this is not the same as saying each player has the same chance of winning in all of those situations, just that each item has the same chance of being the winning item. So formally what this is saying is that if this function f is my basic operation for my magma, then the preimage of any two elements under this operation, in other words, all of the sets of tuples that give you that output, all of those should contain the same amount of tuples which have exactly k entries for any particular k, where this set A sub k is all of the members of the set of n tuples over A, which have exactly k distinct components. The final property is just a non-degeneracy condition that I call non-degeneracy. We're going to say that an operation is f, or an operation is f. An operation f is non-degenerate when its underlying set is has cardinality at least n, where f is an n-ary operation. Oh, I'm sorry. The underlying set should have cardinality strictly greater than n. So This is just basically because if the underlying set has size at most n, then all of the members of the n tuples of A, which have exactly size of A many components, have to have the same set of components. And then it's impossible to have essential polyadicity unless your set is just the trivial one element set. And that sort of ruins everything I'd like to do. So there are variants of rock, paper, scissors with more items that have been played. The French version of rock, paper, scissors adds one more item, which is the well. So the rock and the scissors fall into the well and therefore lose to it, but the paper covers the well and hence defeats it, apparently. So this game is not strongly fair. Some items have a better chance of winning than others, but it is conservative and essentially polyadic. There's also the recent variant called rock, paper, scissors, Spock, lizard, and this is conservative, essentially polyadic, strongly fair, and non-degenerate. So here there are two new items. One is represented by V here for Spock, for Vulcan, and then the L represents the lizard. And so this variant does have all of the properties I would like for a generalized rock, paper, scissors game, although this one is still only for 2 players. Well, our first little result is that the only valid rock, paper, scissors variants for 2 players use an odd number of items. And so formally, we can say this by saying that if we have a selection game A with this arity equal to 2, which is essentially polyadic, strongly fair, and non-degenerate, then if M is the order of this magma, the size of this underlying set of items, then we have to have that number of items is odd. And conversely, for each odd number of items, there does exist such a game. And I'm not going to go through the whole argument, but essentially it comes down to that you need that M divides M choose 2, and that forces oddness. But when you have oddness, then you can also set up the situation that I just described. Notice that actually we didn't need conservativity here. So that particular axiom wasn't necessary to argue this. And this is something that in, there's a graph theory analog of this that's well known. This is a sort of a well understood thing. Okay, so now I'd like to define a pseudo rock, paper, scissors magma as an n-ary magma, which is essentially polyadic, strongly fair, and non-degenerate. So all of the conditions except for conservativity. When A is an n magma of some order M with these properties, I'll say A is a PRPS or pseudo RPS MN magma, and I'll also use those labels to indicate the classes. Now, it turns out that we can actually generalize the previous statement that I discussed before to n-ary, the n-ary situation, which would be like to n-player games. So if we have an n-ary or an n-player, so if we have an n-ary pseudo RPS magma of order M, which again, think we have an n-player game with M items from which to choose, then if we denote by pi of M, this is var pi, if we denote by pi of M the least prime dividing M, then we actually have to have that n is strictly less than pi of M. Or in other words, the number of players must be strictly less than the least prime dividing the number of items from among which we can choose. So, and conversely, for each pair Mn, where M is not 1, I'm also never going to consider M equals 1 because that's trivial. If for each pair Mn with n strictly less than var pi of M, there does actually exist such a magma. And so the argument here is a little bit more involved, but it still is in the same spirit. And really what it comes down to is just that M divides each of these M choose 2, M choose 3, up through M choose n, each of these binomial coefficients. And that really comes from the strong fairness, and also that, I mean, the other properties are also important as well. But yeah, that's where those binomial coefficients are coming from. I need this item, I need each particular item to show up the same number of times when I just consider exactly k many items chosen from my original set. Okay, so now I'd like to talk about RPS magmas. If we have an n-ary magma, which is conservative, essentially polyadic, strongly fair, and non-degenerate, then we're going to say that that is an RPS magma. So in other words, RPS magmas are conservative pseudo-RPS magmas. And so then we'll have similar notation for the collection of all RPS magmas of order M and arity N, which again, we can think of just like the class of all such games, generalized rock, paper, scissors games with N items, or with M items for N players. And we'll also use those terms to indicate the classes. So both the original game of rock, paper, scissors and the game rock, paper, scissors, Spock, lizard are RPS magmas. The French variant is not even a pseudo RPS magma because it's not strongly fair. Well, now I'd like to actually show you how to construct a game for 3 players, since I was concerned with multiplayer versions of rock, paper, scissors, and I haven't shown you that such a thing. I suppose that I've shown you that something similar should exist, assuming that you believe that that result that I stated before, because I did say that pseudo RPS magmas had to exist of the appropriate arity and order. But I'm now going to actually show how to construct a game for 3 players. This is going to be a ternary RPS magma, so a 3-player game, where we have some underlying set A, and we can see from that result that if we need the number of players 3 to be strictly less than the least prime dividing the number of items, then well, we can't use 3, certainly, since the least prime dividing 3 is 3. We can't use 4 because then 2 would be the least prime dividing 4, but 5 is okay. So 5 is the smallest number that's acceptable. So we're going to actually make use of the left addition action of Z5. This is the cyclic group of order 5 under the additive cyclic group of order 5, not the 5-adic integers. We're going to use the left addition action of this guy on itself. So we'll produce an operation that takes 3 tuples of things from Z mod 5 to other things in Z mod 5, which is essentially polyadic. And we're going to actually end up giving this the property that W plus f of x, y, z, so W plus the winner from among x, y, and z, is actually the winner from among W plus x, W plus y, and W plus z for any W that we choose. If it's possible to do that, then we only need to define f on a representative of each orbit of Z mod 5 choose 1, choose 2, choose 3 under the action of Z mod 5. And that's by the essential polyadicity of the operation. So in order to write down the rules for this 3-player game, first I'm going to list the orbits of Z mod 5 choose 1, choose 2, and choose 3 under the action, the left addition action of Z mod 5. So here I have those orbits. The first orbit is just the orbit of the 1 sets. And then, so of course, these really represent, the 1 set 0, the 1 set 1, and so forth. And similarly here, this is the 2 set 0, 1, which doesn't actually have an order, and so on. Okay, so here are all of the orbits. There are 5 of them. Now we're going to choose a representative for each orbit, say the first one in each row of this table. So that's the easiest possible choice. I'll just take my representative to be the first thing I wrote down in this table. Of course, this isn't canonical. I just chose to write down these representatives in this way, but if I've already drawn the table this way, I might as well make that choice. Now I have to choose from each one of these k-sets. I have to choose a representative for each one of my representative k-sets. So I have to actually choose a representative that comes from a set. So for example, if I have 0, 1, 3, then I'm allowed to choose 0 as my designated element. And I could have chosen 1 or 3, but not 2 or 4. And again, this is because this is supposed to be the winning item out of these 3 items. So I have to choose either 0, 1, or 3 to be the winner when 0, 1, and 3 are chosen by the 3 players. And similarly for the other ones. I could have chosen them to be all zeros, but for some reason I chose this to be a 1, which I'm allowed to do. Now we're going to use the left addition action of z mod 5 on itself to extend these choices to all members of the 1, 2, and 3 sets in z mod 5. And so, for example, if I set 0, 1, 3 to go to 0, then adding 1, I obtain the 3 set 1, 2, 4, but then adding 1 to 0, I get 1, and then so on and so forth. We can actually read off a definition for this ternary operation, taking triples from z mod 5 to itself from this table in the following way. So an example should make this clear. We're taking the mapping that sends 2, 4 to 2, this thing that I've drawn here, to indicate that f of any tuple that contains precisely the elements 2 and 4 should be 2. So f of 2, 4, 4 is 2, f of 4, 2, 4 is 2, and so on and so forth through all the possibilities. Okay. I feel like I've been going a little fast, so at this point, are there any questions or comments? I promise I will survive if there are. Okay, I guess there aren't, so I will keep going. So now I've actually written out the Cayley table for this 3 magma, which we obtained from the choice F that I just described. Of course, this really should be a 5 by 5 by 5 array of numbers, but because I'm sort of stuck in 2 dimensions here, I will split it up into 5 separate tables. So in order to read this, if you would like to, for example, this entry indicates that f of 3, 4, 1 is 3. And actually, by the symmetry, even if I had permuted the arguments, it would have given me the same thing. So if you choose to read it slightly differently, you should still be okay. All right, so now I have a formal definition that is the construction that I just gave in that specific case. I don't really want to belabor this too much, because if you understood what I just did, then you essentially understand what this definition is saying. This is just listing out and labeling all of the choices that I just described making. So we start off with some regular group action, which, remember, is an action which is transitive. So anything can get sent to anything else by the action. And it's also free, or fixed point free, which means that the only elements which act trivially are the identity. So if we have a regular group action of group G on some set, then well, we can extend that action in a natural way to K sets in the set of elements of A. And then we can do the same exact thing that we had just done in that example before. We can split the K sets up into orbits. We can choose a representative of each orbit, and then from that representative, we can choose a particular element, which should be the output of that collection of elements under the desired operation. So there is one thing that is necessary in order for this to do what I want it to. We actually need that the extension of this action to each of the sets of K sets is free for each K between 1 and n. So that's the one technicality that we need. Otherwise, this is just describing the thing that I just did. Okay, so assuming that those extensions are free, then we actually have that all alpha action magmas are rock, paper, scissors magmas. And I'm not going to argue that, but it is relatively straightforward. And the place that we get strong fairness is actually that these extensions are free. That's what's going to guarantee us that, that fairness condition that I described before. All right, so a regular RPS magma is then the following thing. If I have some non-trivial finite group G and some n which is strictly smaller than the least prime dividing the order of G, then I'm going to denote by Gn beta gamma the left multiplication action n magma induced by those choices beta gamma, where beta gamma were just all of the choices of orbit representatives and then representatives from within each of those orbit representatives that I had chosen before. So Gn beta gamma is just the alpha action magma corresponding to the regular action of the group on itself, obtained by making some collection of valid choices as per the procedure that I showed you before. So I'm going to refer to such an RPS magma as a regular RPS magma. And now I'm definitely assuming that everything I'm talking about is finite. So I'm not going to worry about infinite groups. Okay, so I'm finally ready to start talking about hypergraphs. Well, a pointed hypergraph for me is going to be a hypergraph. So with some set of vertices S and some set of edges sigma, along with a map that takes edges to vertices, where for each edge, E in my set of edges sigma, G of E is actually in E. And so this is called the pointing of the hypergraph. And for example, if we had, say, if we had the usual 3-vertex cycle viewed as a hypergraph, say by consisting of just all of the unordered pairs in some set, say rock, paper, scissors, choose 2, then a pointing of the hypergraph with these faces or these edges would assign to each edge a particular element. And so, for example, I could assign to the edge rock, scissors, I could assign that, say, rock, since rock beats scissors. And I can view that as actually pointing this edge at, oh, not at scissors, at rock. I can view that as pointing this edge at rock. Now, of course, in the higher dimensional situation, this is not the same as putting an order on the vertices. That's only a special thing that happens in the case that you're looking at a graph or a one-dimensional complex. If I have an edge, or if I have an edge of my hypergraph that has 3 vertices, so like a 2 simplex, then this pointing would assign to, say, rock, paper, scissors, a particular element, rock. And so that's not the same as ordering the edge. That's just pointing the edge at this one point, say rock. All right. Now, I'm going to only really be considering a special kind of hypergraph, which I'll call the n-complete hypergraph on a set S. And so the edge set for this hypergraph is just going to be all of the S choose K for K between 1 and N. So in other words, these are all of the at most n-1 dimensional faces on the simplex of dimension size of S minus 1. Oh, and I should mention that S2 is then going to be just the complete graph on that set of vertices S, where there are loops at all of the vertices. Oh, assuming that you view a loop as being an edge with a single element in it. Right. So then an n hypertournament for me, and I apologize for anyone who studies hypertournaments here, because this is not what is usually referred to as a hypertournament in the literature. But this is what worked for me in this context, and it generalized the correspondence between tournaments and magmas that existed previously in algebra. So an n hypertournament for me is a pointed hypergraph, bold T, which consists of a tournament of the form Sn for some set S, and then a pointing G that can just be an arbitrary pointing. So that's an n hypertournament for me. And if you look at what this says in the n equals 2 case, then you will actually get a one-dimensional graph tournament in the usual sense. So in this example here of the 3-player game I constructed with 5 items to choose from, we have a table here that lists out all of the k sets for k equals 1, 2, or 3, and then what the corresponding pointing of those k sets is. And so this is also the data that we need to define a corresponding 3 hypertournament in this case. And so you can probably see from this example that the data that I needed to define a 3-player RPS magma was actually precisely the same data, just presented slightly differently, that I need to define a 3 hypertournament. Now, of course, I can go back and forth between these two concepts. If I have an n hypertournament, then I can obtain a hypertournament magma by constructing an n magma A, where for any collection of elements of my tournament, I'm going to define f of u1 up through un to just be the pointing of the edge containing the vertices u1 up through un, which could be of any size between 1 and n. So I could have equivalently actually defined a hypertournament magma to just be an n magma, which is conservative and essentially polyadic. So algebraically, that's the same type of object. So tournaments, which would be the n equals 2 case of a hypertournament, as I've defined it, have been studied for a long time. Hederlin and Schwadl introduced the n equals 2 case in 1965. And there's been a lot of work in the intersection of universal algebra and combinatorics on varieties generated by tournament magmas. So I actually found the survey by Svenkovic and et al. Very helpful in writing this paper on rock, paper, scissors. There are algebraic motivations for everything I'm going to do from now on, but I won't get into them right now. I just want to throw it out there that some of this is actually algebraically motivated, but it's still going to be nice on its own, I think. So I'd like to talk about an embedding result for these hypertournaments. So first of all, let's consider this really nice class of hypertournaments. We're going to say that a hypertournament is a regular balanced hypertournament when the hypertournament magma for this tournament is a regular rock, paper, scissors magma. So these are just the tournaments, the hypertournaments that correspond to regular rock, paper, scissors magmas, which are the ones that are constructed by that group action construction that I described before. And those, I guess I should mention, those are not all possible RPS magmas. There are RPS magmas which are not regular. So it would be very nice if each finite n hypertournament embedded into a finite regular balanced hypertournament. And this turns out to be the case. I don't know whether or not that seems plausible at first glance, but it can be done. And I will now show you how. So in order to do that, I'm going to need to actually present regular RPS magmas in a slightly different way. That's maybe a slightly more sophisticated way of looking at them. So first note that in the binary case, this regular RPS magma, so some group G, this 2 just indicates binary, and then for these choices beta and gamma of orbit representatives and then elements from each of those representatives, we have that f of the identity and some element x is the same thing as x times f of x inverse E, where now I'm using multiplicative notation as opposed to the additive notation I was using before. So as we would say in the case of tournament graphs or tournament digraphs, either E has to dominate X or E has to dominate X inverse. And exactly one of those has to take place. So either E beats X or E beats X inverse, exactly one of those has to hold. So then note that the orbit of a pair of elements X, Y under the regular action of a group on itself contains the identity paired with some X inverse Y. And okay, yeah, so this orbit contains the identity paired with this guy. And also, oh, I've lost my braces here. Okay, yes. So the orbit of XY contains the identity paired with X inverse Y and also the identity paired with Y inverse X, which are inverses. We need only define a map lambda specifying for each pair of inverses whether E dominates X or E dominates X inverse in order to specify all of these choices beta gamma. So it turns out that is actually precisely the data that's necessary. So we can think of this choice function lambda selecting from each pair X inverse which one E dominates as choosing the positive direction with respect to X and X inverse. Oh, and in case you're worried for a second, remember that RPS magmas have to have odd order. And so we can't have any weird order 2 elements obstructing us from choosing from among the 2 distinct elements X and X inverse. Now, I need to do this not for 2 pairs of elements, but for k sets of elements in a group. So I'm going to need an analogous thing for k sets where this is going to be sort of an n-ary analog of inverse elements for a group element. And so I call these things obverses. So if we have some finite group and some n where n is smaller than the least prime dividing the order of the group, and we choose some k between 1 and n minus 1, and take k sets of non-identity elements in the group, say u and v, we're going to say that v is an obverse of u when it's possible to pick one element out of u, say ai, and then multiply the others by ai inverse, and then toss in ai inverse itself, and that will give us v. So if it's possible to start with u, perform this process for some ai, and then get v, that's what it means for u and v to be obverse k sets. So the set of obverses, so obv is the set of all obverses v of u, as well as u itself. So we're just going to also declare that u is an obverse k set of itself. Or well, maybe not an obverse k set, but it's going to be in the set of obverses for convenience. So the obverses of a set U are the non-identity elements in the members of the orbit of U along with the identity, which are not just the set U union with the identity, which contain the identity. So in order to specify a regular rock, paper, scissors magma, it suffices to choose a member of each collection of obverses for which the identity dominates that collection. And so I'm going to call such a choice among for each collection of obverses an n-sign function. So this is going to be, so an n-sign function is going to be a choice function on the collection of all obverses for any possible collection of obverses that we could form up to size at most n-1. And so then we're going to refer to a member of this as an n-sign function, as I think I just said as well. And so we'll write gn lambda instead of gn beta gamma to refer to gn as just being constructed from the sign function. And I'm definitely gliding over some details, but it turns out that these things are equivalent, and this is a much cleaner way to present a regular RPS magma or its corresponding hypertournament. Now we can finally give this embedding result, which says that any finite hypertournament with no other constraints on it can be embedded into a finite regular balanced hypertournament, which is one that comes from an RPS magma. So take T to be some finite hypertournament. The group I'm going to use is the direct sum of cyclic groups whose orders are alpha U, where this alpha U has to have the property that n is strictly less than the least prime dividing alpha U, and this is possible to accomplish. I'll give examples in a little bit. So we're then going to take an n-sign function lambda for this group, which have to exist as well, well, just because they're choice functions. I mean, that's not really technical. Okay, so then we're going to define for when the pointing of this k set, u1 through uk, is u1, which you can relabel so that this is always the situation. We're going to define that the sign function on this set of obverses of all of the collection of ui minus u1, where I is not 1, the collection of all the differences, the element that we choose the identity to dominate is this collection. And so it turns out that this is actually a well-defined map, and that the n hypertournament corresponding to this gn lambda for this particular choice of lambda has to contain a copy of the hypertournament T. And any values might be chosen for the other orbits. There are other orbits, but it's impossible for these choices that I've described here to interfere with each other. And so if you want a specific class of finite regular balanced hypertournaments in which any finite hypertournament embeds, sometimes I write tournament, but of course I mean hypertournament. I just get tired of saying hyper all the time. We need only use magmas of the form gn lambda, where G is either, I guess, a vector space over a finite field is a nice way of putting it. So G is the mth direct power of some z mod kappa of n, where kappa of n is the least prime strictly greater than n. So that's one choice, as vector spaces over finite fields if you want to be prosaic. So assigning a direction to each possible non-zero vector in those spaces. Or the other choice we have are just cyclic groups of the appropriate order. So what we can do is we can take our group to be z mod alpha of m, where alpha of m is the product of all of the primes of the appropriate number of primes, starting with the prime that is the least prime greater than strictly greater than n. So we can also actually produce a cyclic group by just choosing a bunch of different primes, starting with the next biggest one past n. All right. So in particular, every tournament of order m, and so here I do actually mean binary binary tournament, so two tournament, embeds into the tournament corresponding to some regular RPS magma of the form z mod 3 to the m 2 lambda. So this tells us that any tournament of order m embeds into some balanced tournament of order 3 to the m. Well, now I want to talk about how optimal that is. So first of all, I never defined what a balanced hypertournament was. I just told you what a regular balanced hypertournament was. We're going to say that a hypertournament is balanced when the hypertournament magma of T is just an RPS magma. So we're dropping the regular group action construction, but we're leaving on that strong fairness and the other properties as well. Well, if we let h sub n of m denote the least natural so that each n hypertournament of order m is contained, as in can be embedded in, some balanced n hypertournament of order hn of m, then our previous observation is that h2 of m is at most 3 to the m, that you can always fit every n-ary hypertournament, which is just the usual tournament of order m, into some tournament of order 3 to the m. You might have to use different tournaments of order 3 to the m for different tournaments of order m, but some tournament of 3 to the m of order 3 to the m will suffice. We can actually do much better than this. So every tournament of order m actually embeds into a balanced tournament of order 2m plus 1. And so this is much better than 3 to the m. And I'm going to argue this to you by way of an example. So let's say that I want to start off with this tournament where let's say I have this. So this is not a balanced tournament. This is just some tournament on 3 vertices, which I will call A, B, and C. I need to construct a balanced tournament. So that's a tournament where every vertex has the same out degree and in degree. That's equivalent to what I defined previously. And so in order to do that, what I'm going to do is perform a doubling construction. So I'm going to write another copy of this tournament over here with the same dominance relation. So we're still going to have that A dominates B, B dominates C, and A dominates C. And then I'm going to label each of these guys to distinguish them. This is the 1 copy, this is the 2 copy. And so then I'm going to add in 1 new vertex, which I call eta. And then I'm going to do the following thing. Since B1 dominates C1, I'm going to have its partner, C2, dominate B1. And then similarly, since A1 dominates B1, B1 gets to dominate A2, which is the partner of A1. And so either you're dominated in the first copy and you dominate the partner in the second one, or vice versa. Okay, so now I still have to resolve whether B1 dominates B2 or vice versa. And so no matter what I choose, one of them will have a bigger out degree than the other one. And so that's where this extra vertex eta comes in. So then if I'm going to look at B2, or B1 and B2, I'll say choose that B1 dominates B2, but then B2 will dominate eta, which makes up for that. And then eta in turn dominates B1. Now, of course, I haven't drawn in the edges, but I've described at this point everything that needs to be done to the vertex B1. And you can imagine that you could do the analogous thing for every other vertex, and that this is actually true in general. So one can actually show by example that H2 of M is at least 2M minus 1. There's an example that you can see it has to be at least this much. And a similar construction to the one I gave previously, which is just slightly more clever than that, shows that H2 of M is actually at most 2M minus 1. And so H2 of M is precisely 2M minus 1. That's the exact value. I only produced the construction given for general hypertournaments once I found that I couldn't see how to generalize the doubling construction from the n=2 case. There's just too much going on. I couldn't see how to generalize that. It would be really interesting to know whether the argument I gave in the n=2 case can generalize to the higher arities. By the general embedding result, we know that Hn of m is at most kappa of n, where remember this is the least prime strictly greater than n to the mth power. And so again, this is those parentheses are there. So for n strictly greater than 2, is this the best bound possible? And actually, since I ended up doing this right at the end of this project, I haven't really thought too much about, are there even some easy examples like in the n=2 case, which give a lower bound? The obvious choice would be an n hypertournament where a single vertex dominates every other collection of vertices, or in other words, that the pointing function is just a constant valued function. Yeah, but I don't, actually, well, okay, it can't be a constant value function. I'm sorry, now I'm thinking about this more. Yeah, but okay, there is some analogous trivial example to the one that I have in mind, but I'm not sure what the bound is that it gives. All right, so I suppose this is where I will stop. Thank you very much for your attention.
Let's thank the speaker.
Okay, thank you. Right.
I will stop the recording and we'll take questions.